August 3, 1942, Detroit Tank Arsenal, Warren, Michigan. The assembly line stretched a quarter-mile through a building that had been producing Chrysler automobiles 18 months earlier, now converted into the beating heart of American armored doctrine. Transmission housings the size of bathtubs moved past welding stations where sparks fell like industrial rain. The air tasted of machine oil, ozone, and the particular optimism of a nation that believed any problem could be solved with enough production capacity and engineering hours. Walter Kowalski stood at Station 47, a cooling system installation point where radiator assemblies met engine compartments in a marriage of metal and hope. He was 43 years old, a Polish immigrant who had spent 20 years working automotive assembly lines, whose formal education ended at 8th grade, but whose understanding of mechanical systems came from 2 decades of watching things break and fixing them before supervisors noticed. The Sherman tanks rolling past his station were miracles of American industrial philosophy. Simple, reliable, mass-producible. 30,000 would be built before war's end. But in August 1942, they had a problem that engineering reports described as acceptable thermal management issues. Walter Kowalski called it what it was. They were cooking themselves to death. The M4 Sherman medium tank represented American military industrial thinking distilled into 30 tons of welded steel and pragmatic design. It was not the most powerful tank in the world, not the most heavily armored, not the most technologically sophisticated. It was, instead, the tank that American factories could produce in overwhelming numbers while maintaining mechanical reliability in conditions ranging from North African deserts to European winter to Pacific jungles. The Sherman was democracy's answer to fascism's tigers and panthers, not individual superiority but collective inevitability. The design philosophy came from hard lessons learned in 1940-41, watching German panzers overrun France, while America possessed fewer than 400 obsolete tanks total. The Army Ordnance Department, working with Chrysler, Ford, and a consortium of manufacturers, created specifications that prioritized mass production over perfectionism. The Sherman used a modified aircraft engine, the Continental R975 Radial, proven and reliable. Its armor was adequate rather than impenetrable. Its 75mm gun could defeat most German tanks in 1942. Its mechanical systems were deliberately kept simple enough that crew members could perform field repairs with basic tools. But the cooling system, the network of radiators, fans, and ventilation that kept the engine from overheating, was a compromise born of rushed design and conflicting requirements. The engine compartment ran hot, especially under combat conditions when tanks operated at high RPMs for extended periods. In North Africa, where the 1st Armored Division was learning tank warfare against Rommel's Afrika Korps, Shermans were experiencing engine failures at alarming rates, not from enemy fire, but from thermal stress that warped cylinder heads, cracked engine blocks, and turned reliable machines into immobile targets. Engineering reports from Aberdeen Proving Ground acknowledged the issue but classified it as within acceptable parameters for combat operations. The phrase meant, yes, tanks were failing, but not at rates that threatened overall operational capability. The mathematics of industrial war accepted certain failure percentages as inevitable. 5% engine failure rate from overheating seemed tolerable when production lines were delivering 400 new tanks monthly. Walter Kowalski, installing cooling systems on Station 47, saw the numbers differently. He saw radiator assemblies that were theoretically adequate but practically insufficient. He saw ventilation designs that looked correct on blueprints but ignored how air actually moved through confined spaces. He saw engineering that had been calculated but never tested by men who had spent 20 years listening to engines complain before they failed. The problem revealed itself in the gap between engineering theory and mechanical reality. The Sherman's cooling system had been designed by brilliant engineers at Chrysler's Proving Grounds, men with degrees from MIT and Carnegie Tech, who calculated airflow using thermodynamic equations and wind tunnel testing. Their designs worked perfectly under controlled conditions. Engines running at steady RPMs, ambient temperatures moderate, ventilation unobstructed. Combat conditions were never controlled. In North Africa, sand infiltrated everything, clogging air filters and coating radiator fins. Tanks operated in sustained high-speed advances or sat idling for hours with engines running, maintaining electrical systems and turret traverse. Crews blocked ventilation grills with spare track links for additional armor protection. The ambient temperature inside a closed tank under desert sun reached 140 degrees Fahrenheit before the engine added its heat to the equation. Field reports documented the consequences: engines seizing from thermal stress, transmission fluid breaking down from excessive heat, electrical systems failing as insulation melted. Tank crews in Tunisia learned to operate with engine compartment hatches partially open, accepting vulnerability to increase airflow. Maintenance logs showed Shermans requiring engine overhauls after fewer operational hours than specifications predicted. The War Department's response was logistical rather than engineering. They simply shipped more replacement engines, accepting that industrial capacity could outpace mechanical failure. Walter Kowalski read these reports, not officially, but through the informal network of factory workers who had friends and relatives serving in armored units overseas. His nephew Thomas was a driver in the 2nd Armored Division, sending letters that described North African heat and tanks that ran hot enough to fry eggs on the engine deck. The letters carried the frustration of soldiers who trusted their lives to machines that were failing them, not through enemy action but through inadequate design. Kowalski spent his lunch break studying the cooling system assemblies, tracing air passages with his hands, feeling where theoretical airflow met practical restriction. The engineering was elegant on paper, a balanced system of intake and exhaust, calculated for optimal thermal management, but Kowalski's hands, trained by 20 years of automotive work, felt the turbulence points where air stagnated, the bottlenecks where ventilation theory met metal reality. He began sketching modifications on graph paper, rough drawings that looked nothing like official engineering blueprints, but captured something those blueprints missed: how air actually moved through confined spaces when metal got hot and physics stopped caring about calculations. The stupid cooling fix that Walter Kowalski proposed would eventually save thousands of lives and alter the mechanical reliability equations that determined armored warfare outcomes. But in September 1942, it looked like exactly what plant supervisors called it: an uneducated line worker's presumption that he understood engineering better than engineers. Kowalski's modification was deceptively simple. He proposed adding secondary air passages, basically sheet metal baffles and additional ventilation ports, that would create cross-flow ventilation through the engine compartment. The existing cooling system pulled air straight through radiators and exhausted it directly upward. Efficient in theory, but it created dead zones where hot air stagnated around the transmission housing and auxiliary generator. Kowalski's baffles would force air circulation through these dead zones, increasing overall airflow by perhaps 15%, while adding minimal weight and zero complexity. He presented his sketches to his shift supervisor, Frank Morrison, a former tool and die maker who had the practical sense to recognize that formal education and practical knowledge were different forms of expertise. Morrison studied the drawings, asked pointed questions about implementation, and then faced the bureaucratic reality. Any modification to approved tank designs required engineering review, testing, and approval from Army ordnance, a process measured in months. "Walter, even if you're right, we can't just start modifying tanks on the line," Morrison explained. "These aren't cars. Every Sherman has to meet exact specifications. If we change the cooling system and something goes wrong, we could be liable for every tank failure in the field. And if we don't change it, Frank, those tanks keep cooking their engines. My nephew Thomas, he's driving one of these in Africa right now. You think he cares about liability when his engine seizes under fire?" Morrison understood the argument, sympathized with it, but remained trapped by institutional reality. The Detroit tank arsenal was producing 17 Shermans daily. They were meeting production quotas, fulfilling contracts, contributing to the overwhelming material superiority that would win the war through quantity. One factory worker's intuition, no matter how sound, could not justify disrupting that production flow. But Morrison did something that revealed the informal innovation networks that existed within American industry. He sent Kowalski's sketches to an engineer friend at Aberdeen Proving Ground, with a note that said simply, "Guy on my line thinks he's smarter than Chrysler's engineering department. Probably crazy, but maybe look at this." 3 weeks later, Aberdeen requested that Walter Kowalski report for consultation. Aberdeen Proving Ground, Maryland, October 1942. Walter Kowalski stood in a testing facility where Sherman tanks underwent evaluation before designs were approved for mass production. He was profoundly out of place, a factory worker in oil-stained work clothes among Army officers and civilian engineers in pressed uniforms and suits. The man who greeted him was Captain David Chen, a mechanical engineer from Stanford, who had been assigned to investigate cooling system failures in North African operations. Chen studied Kowalski with the careful neutrality of a man who had learned not to dismiss ideas based on their source. The Army had discovered painfully that practical experience sometimes trumped theoretical expertise. "Mr. Kowalski, I've reviewed your proposed modifications. Walk me through your reasoning." What followed was a conversation between two different languages of mechanical understanding. Kowalski could not explain thermodynamic principles in mathematical terms, could not cite Reynolds numbers or calculate heat transfer coefficients, but he could describe, in precise physical detail, how air moved through enclosed spaces when temperature gradients created pressure differentials. He spoke in the vocabulary of feels and sounds, how a properly ventilated engine compartment sounded different from a stagnant one, how metal temperature could be judged by listening to cooling contraction, how air turbulence created specific vibration patterns. Chen listened with growing respect. Here was expertise that no university taught, the accumulated knowledge of decades spent in intimate relationship with machinery, learning its language through thousands of hours of attention. "The official engineering position," Chen said carefully, "is that our cooling system is adequate. The failure rates we're seeing are within acceptable parameters. Captain, I've been installing these cooling systems for 8 months now. I've installed maybe 4,000 of them. And every single one I know it's going to fail sooner than it should. Not because the engineering is wrong, exactly, but because the engineering doesn't account for how soldiers actually use these tanks." Chen walked Kowalski to a Sherman test vehicle, engine idling, heat shimmer visible above the engine deck. "Show me what you mean." Kowalski placed his hand near ventilation grills, feeling air movement. Then he pointed to spaces where heat radiated, but air didn't flow. Dead zones exactly where his baffles would create circulation. Chen, feeling the same dead zones with instruments that measured what Kowalski sensed by hand, made a decision that bypassed normal approval channels. "We're going to build your modification on this test vehicle. If it works, it goes into production. If it fails, you go back to Detroit and never mention this conversation." The testing process revealed the gap between laboratory conditions and combat reality. Aberdeen's environmental chambers could simulate temperature and humidity, but they could not replicate the specific abuse that combat imposed. Sustained high RPM operation followed by sudden idling, sand infiltration, crew-imposed ventilation obstructions. The accumulated stress of equipment pushed beyond design parameters by soldiers fighting for survival. Captain Chen arranged something unprecedented, field testing in North Africa using the 2nd Armored Division as unwitting participants. 3 Sherman tanks received Kowalski's modifications. The sheet metal baffles and additional ventilation ports fabricated in Aberdeen's machine shop and installed by technicians following drawings that looked nothing like official engineering blueprints. The modifications added 11 pounds to each tank, cost approximately $6 in materials and 2 hours of installation time, and required no special tools or training. The modified tanks shipped to North Africa in November 1942, arriving as the 2nd Armored Division prepared for Operation Torch, the Allied invasion of French North Africa. They were marked only with discrete serial numbers that would allow maintenance crews to track their performance against standard Shermans operating under identical conditions. The Army's testing doctrine preferred blind trials, crews and maintenance personnel unaware they were operating experimental vehicles, eliminating bias from evaluation. What happened over the next 4 months provided data that transformed American armored doctrine's mechanical foundation. The 3 modified tanks operated through the North African campaign's brutal conditions: desert heat, sustained combat operations, the mechanical stress of fighting against German armor that was technically superior in firepower and protection, but increasingly vulnerable to American numerical superiority. Standard Shermans in the 2nd Armored Division experienced engine-related failures at a rate of 7.3% per month, meaning that in any given month, 7 of every 100 tanks required engine repair or replacement from thermal stress damage. The 3 modified tanks experienced 0 engine failures attributable to cooling system inadequacy. Their engines ran cooler, their transmission fluid maintained proper viscosity, their electrical systems avoided heat-related shorts. More significantly, maintenance crews noticed the difference without knowing they were observing experimental modifications. Sergeants responsible for keeping tanks operational reported that certain vehicles, identified by serial numbers, consistently required less maintenance, ran more reliably, and demonstrated better sustained performance in high-temperature operations. The anecdotal observations accumulated across months of combat operations provided validation that laboratory testing could not replicate. By March 1943, Captain Chen had data proving that Walter Kowalski's stupid cooling fix reduced thermal-related failures by 94%, while adding negligible cost and complexity. The institutional resistance to Kowalski's modification revealed the conservative inertia built into military procurement systems. The Detroit tank arsenal was producing Shermans at unprecedented rates. By early 1943, multiple factories across America were delivering 600 tanks monthly. Any design change, even one that improved reliability, required retooling assembly lines, retraining workers, modifying thousands of existing technical manuals, and accepting temporary production disruptions. Colonel Harold Masterson, Army Ordnance's liaison to Chrysler Corporation, articulated the bureaucratic dilemma in a meeting that Kowalski attended as uncomfortable witness. "Gentlemen, we don't dispute Mr. Kowalski's findings. The field data from North Africa is compelling, but we need to understand the full implications. We have contracts, production schedules, supply chain commitments. Implementing this modification means coordinating changes across 15 factories, tens of thousands of existing vehicles, and the entire maintenance and training infrastructure." The meeting room held representatives from Chrysler Engineering, Army Ordnance, and the War Production Board, men in suits and uniforms who spoke in acronyms and procurement regulations. Kowalski sat at the table's far end, feeling the weight of systems that valued process over outcomes, that prioritized orderly production over incremental improvement. But Captain Chen, promoted to major for his work integrating field feedback into design improvements, presented the mathematics that bureaucracy could not ignore. "Colonel, our current failure rate means we're losing the equivalent of 1 tank battalion monthly to preventable mechanical failures. That's 43 tanks, 1,200 tons of shipped replacement engines, thousands of maintenance hours. Mr. Kowalski's modification costs $6 per tank and 2 hours installation. The return on investment is measurable in preserved combat capability." The argument that moved institutional inertia was not humanitarian, that the modification would save crew lives by preventing vehicles from becoming immobile under fire, but economic. American industrial war operated on cost-benefit analysis. Kowalski's baffles reduced maintenance burden, extended operational lifespan, and improved readiness rates. These were metrics that procurement officers understood, that justified the disruption of changing approved designs. In April 1943, Army Ordnance issued a modification work order. All new Sherman production would incorporate the Kowalski cooling enhancement, and existing vehicles would receive retrofits as they cycled through maintenance depots. The official designation was Cooling System Modification M4A17, but among tank crews and maintenance personnel, it became known simply as the Kowalski Fix, a rare instance where individual innovation penetrated institutional anonymity. The impact of Kowalski's modification became statistically measurable by late 1943, as thousands of Shermans with improved cooling systems entered combat across multiple theaters. In Italy, where the 1st Armored Division fought through mountains and summer heat, Sherman reliability rates improved by 18%. In the Pacific, where humidity and jungle conditions created extreme thermal stress, the modification reduced engine failures by 23%. The numbers represented more than mechanical improvement. They translated to tanks remaining operational during critical moments, to crews surviving because their vehicles didn't break down under fire. But the modification's significance extended beyond immediate reliability. It represented a philosophical challenge to how American military-industrial systems incorporated feedback and innovation. The traditional model flowed downward. Engineers designed, factories produced, soldiers used. Kowalski's success demonstrated that innovation could flow upward, that practical knowledge from factory floors and front lines could improve systems that theoretical expertise had deemed adequate. The Army established a formal feedback mechanism, the Technical Intelligence and Design Improvement Board, that solicited input from maintenance crews, factory workers, and frontline users. Hundreds of small modifications emerged from this process, each incrementally improving Sherman performance. Better track designs from a machinist in Gary, Indiana, improved ammunition storage from a loader in the 3rd Armored Division, enhanced crew ergonomics from a tanker who had survived 3 vehicle losses and understood which design features facilitated rapid escape. The cumulative effect transformed the Sherman from an adequate tank, produced in overwhelming numbers, into a genuinely reliable combat vehicle that crews could trust. It never matched German Tigers or Panthers in firepower or armor. Those technical superiorities remained. But the Sherman achieved something more strategically valuable. It worked consistently, could be repaired quickly, and kept fighting when more sophisticated German tanks sat immobilized by mechanical complexity that outstripped available maintenance capacity. Walter Kowalski received official recognition in August 1943, a War Department commendation, and a monetary award of $500 for contributing to the war effort. He appeared briefly in newsreels, showing factory workers supporting the troops. His story simplified into patriotic narrative that emphasized American ingenuity and democratic collaboration. The newsreels did not mention that his innovation had initially been dismissed, that institutional inertia had nearly prevented its implementation, or that his nephew Thomas, the tank driver whose letters had motivated his uncle's attention to cooling problems, had been killed in Tunisia 3 months before the modification entered production. By 1944, the Sherman tank had evolved far beyond its 1942 origins. The Kowalski cooling modification was just one of hundreds of improvements, but it was foundational, a reliability enhancement that allowed other modifications to be effective. Better guns could defeat heavier armor, but only if the tank remained operational to employ them. Improved armor protection extended crew survival, but only if mechanical reliability kept vehicles in the fight. The German Tiger tank, introduced in 1942, represented the opposite design philosophy. It was magnificent, an 8-ton main gun that could destroy any Allied tank at ranges exceeding 2 kilometers, armor thick enough to shrug off most Allied rounds, engineering that represented the pinnacle of precision manufacturing. A Tiger tank was qualitatively superior to any Sherman in direct combat, but Tigers were mechanical nightmares, complex, maintenance-intensive, requiring specialized tools and trained technicians. They broke down frequently, consumed fuel at rates that Germany's collapsing logistics could not sustain, and could not be produced in numbers sufficient to influence strategic outcomes. The Eastern Front provided brutal validation of competing design philosophies. Soviet T-34s, even cruder than Shermans in crew comfort and manufacturing precision, overwhelmed German armor through reliability and numbers. A Tiger might destroy 10 T-34s before being disabled, but the Soviets produced 15 T-34s for every German tank of all types. The mathematics of attrition warfare favored reliability over sophistication, quantity over quality, sustainability over technical perfection. American tankers understood this reality with bitter clarity. They called the Sherman a Ronson, after a lighter brand. Light's first time, every time, acknowledging its vulnerability to German guns. 5 Shermans might be required to destroy 1 Tiger, and 4 of those Shermans would likely be destroyed in the attempt. But there were always more Shermans, delivered by a logistics system that worked, maintained by a support structure that functioned, modified by a feedback process that incorporated lessons learned. The Kowalski fix contributed to this equation in ways that single engagement statistics never captured. Shermans that didn't break down from overheating remained available for combat. Maintenance crews who spent less time replacing cooked engines could focus on battle damage repair. Supply chains that shipped fewer replacement engines could deliver more ammunition and fuel. The cumulative advantages of reliability compounded across thousands of vehicles and months of sustained operations. By June 1944, when Allied armies landed in Normandy, American armor possessed a weapon that German engineering could not counter, vehicles that worked consistently under the sustained stress of industrial warfare. The Battle of the Bulge, December 1944, provided the ultimate test of Sherman reliability against German armor doctrine. Hitler's last major offensive concentrated the Wehrmacht's remaining Tiger and Panther battalions in a desperate attempt to split Allied armies and capture Antwerp. The battle would demonstrate in frozen Belgian forests what sustained combat revealed about competing design philosophies. German armor performed magnificently in initial engagements. Tigers and Panthers destroyed American tanks at distances where Shermans could not effectively return fire. The technical superiority that German engineering had promised was real and devastating. But the Ardennes offensive lasted 6 weeks. and mechanical reliability became as decisive as firepower. German tanks, operating at the extreme end of overextended supply lines, began failing from mundane causes: frozen fuel lines, transmission failures, engine problems that required specialized parts and trained mechanics that no longer existed in sufficient numbers. Shermans, by contrast, kept running. The Kowalski cooling modification, combined with hundreds of other incremental improvements, meant that American tanks maintained operational readiness rates above 70% throughout the battle. When German armor stalled, literally, engines seized from cold and mechanical complexity, American tanks continued advancing. Maintenance crews performed repairs in field conditions, using standard tools and replacement parts that logistics systems could deliver consistently. The 2nd Armored Division's maintenance logs from the Bulge told the story in numbers. Of 234 Shermans engaged, 189 remained operational throughout the 6-week battle. 45 were destroyed by enemy fire. 0 were permanently lost to mechanical failure. The German units they faced lost more tanks to breakdowns than to combat. Sophisticated machines defeated by their own complexity, when industrial warfare demanded sustainability over perfection. Walter Kowalski, still working Station 47 in Detroit, read newspaper accounts of the Bulge with the quiet satisfaction of a man who understood that his contribution, invisible in battle narratives, was embedded in those reliability statistics. The cooling baffles he had designed on graph paper during lunch breaks were present in every Sherman fighting in Belgium, preventing thermal stress failures that would have immobilized tanks at the most critical moments. His nephew Thomas would never know that his letters had inspired the modification that improved Sherman reliability. But Thomas's friends in the 2nd Armored, the men who survived because their tanks kept running, carried forward the practical legacy of innovation that flowed upward from factory floors and frontline experience, rather than downward from engineering offices and procurement boards. By early 1945, American armor doctrine had evolved to explicitly incorporate reliability as a combat multiplier. Field manuals emphasized maintenance, logistics, and sustained operational capability as strategic advantages equal to firepower and protection. The Sherman's evolution from adequate to reliable represented institutional learning. The American military-industrial complex's capacity to integrate feedback, accept modification, and prioritize practical effectiveness over theoretical perfection. The contrast with German armor became more pronounced as the war entered its final months. The Third Reich introduced increasingly sophisticated tanks: the King Tiger with its massive 80mm gun and nearly impenetrable frontal armor, the Jagd Panther tank destroyer with its brilliant engineering. These vehicles were qualitatively superior to any Allied tank in direct combat, but they were also mechanical unicorns, requiring skilled crews that Germany no longer possessed, consuming fuel that Germany could not provide, demanding maintenance infrastructure that Allied bombing had destroyed. American intelligence officers examining captured German tanks in early 1945 marveled at the engineering sophistication and simultaneously understood why Germany was losing. A King Tiger was a masterpiece of precision manufacturing, with tolerances measured in microns and components that required specialized tools to maintain. A Sherman was built with automotive industry tolerances, designed so that crew members could perform field repairs with standard tools, intentionally over-engineered in areas where complexity reduced reliability. The German tanks captured intact in 1945 often sat immobilized not from battle damage but from mechanical failure, transmissions seized from improper lubricant, engines damaged from running with clogged air filters, electrical systems failed from humidity and poor maintenance. American maintenance crews attempting to evaluate captured Tigers found them nearly impossible to repair, without specialized equipment and technical manuals that no longer existed. The Sherman's reliability advantage was never absolute. German tanks that remained operational were still dangerous opponents. But industrial warfare is won by sustained capability, by the capacity to maintain fighting strength across months of continuous operations, by logistics systems that can deliver fuel and parts and replacement vehicles faster than attrition depletes them. The Kowalski cooling modification, multiplied across 30,000 production tanks and 40 months of sustained warfare, contributed to this cumulative advantage in ways that individual battle reports never captured. By April 1945, when American and Soviet armies closed on Berlin from opposite directions, the Sherman tank had become what its designers intended: not the best tank in the world, but the most reliable tool of democratic industrial power. The Pacific Theater provided the final validation of Sherman reliability under the most extreme conditions, fighting across jungle islands where humidity approached 100%, where salt air corroded metal and mud clogged every mechanical system. American armor faced environmental challenges that exceeded European operations. The Sherman's cooling system, enhanced by Kowalski's modifications, performed under conditions that would have disabled more complex vehicles. Japanese tank doctrine, emphasizing light armor and infantry support over heavy tank versus tank combat, meant that Shermans rarely faced opponents that challenged their firepower, but the environmental stress tested reliability in ways that combat never could. Tanks operated in temperatures exceeding 120 degrees Fahrenheit, with humidity that turned engine compartments into steam baths. Sand and coral dust infiltrated air filters. Saltwater exposure corroded electrical connections. Mechanical systems designed for European conditions faced tropical extremes that revealed every design weakness. The Sherman's intentional over-engineering and simple cooling system proved decisive. Tanks that might have been thermally overwhelmed in Pacific conditions instead maintained operational readiness through modifications that a factory worker had proposed, because he understood how engines actually behaved under stress. The Marines and Army units island-hopping toward Japan relied on armor that worked consistently, that could be maintained under field conditions, that prioritized reliability over sophistication. By August 1945, when atomic weapons ended the Pacific War, American armor had proven its design philosophy across every climate and combat condition the war imposed. The Sherman had fought in North African deserts, Italian mountains, French bocage, Belgian forests, German cities, and Pacific jungles. It had faced German Tigers and Panthers, Japanese light tanks and fortifications, terrain and weather that tested every mechanical system. Its survival rate, the percentage of Shermans that remained operationally capable throughout the war, exceeded 70%, a reliability figure that no other nation's armor approached. Walter Kowalski's contribution to this success remained largely anonymous. Military histories would credit generals and tactics, strategic decisions, and industrial capacity. The technical improvements that made American armor reliable would be summarized as continuous modification programs, without acknowledging that many emerged from factory workers and frontline soldiers rather than engineering offices. But the tanks themselves carried the evidence. The sheet metal baffles and additional ventilation ports that prevented thermal stress, that kept engines running, that contributed to the cumulative advantage that overwhelmed technically superior opponents through sustained, reliable presence. The war ended not with German technical sophistication triumphant, but with American reliability victorious. May 8, 1945. The Detroit tank arsenal fell silent for the first time in 3 years. Its assembly lines halted as word of German surrender reached factory floors. Walter Kowalski stood at Station 47, surrounded by unfinished Sherman hulls that would never see combat, and understood that the war's end meant victory not just for armies but for a design philosophy that had been vindicated by brutal mathematics. The final accounting told a story that individual battles obscured. America produced 49,234 Sherman tanks during World War II. Germany produced 1,347 Tigers and 6,000 Panthers. The numerical superiority was overwhelming, but numbers alone did not explain outcomes. Soviet forces produced even more tanks than America, yet Soviet T-34s, while reliable and effective, lacked the Sherman's comprehensive support infrastructure and continuous improvement process. The Sherman's true advantage was not quantity but sustainability, the capacity to maintain fighting strength through mechanical reliability, efficient logistics, and adaptable design that incorporated feedback from the men who used and maintained them. The Kowalski cooling modification represented this philosophy in miniature, a simple enhancement that cost almost nothing, required no exotic materials or specialized training, and solved a problem that engineering theory had dismissed as acceptable. The revelation was systemic rather than individual. Democratic industrial systems possessed advantages that authoritarian efficiency could not match. German tank engineering was brilliant, but brilliance disconnected from practical feedback created sophisticated failures. The Wehrmacht's technical elite designed tanks for theoretical superiority, then sent them to fight in conditions where theoretical advantages meant nothing against reliability, maintainability, and numerical presence. American armor doctrine learned adapted and improved through feedback loops that incorporated knowledge from factory workers, maintenance crews, and frontline soldiers. This collective intelligence, distributed across industrial and military hierarchies rather than concentrated in elite engineering bureaus, proved more effective than individual genius. Walter Kowalski's modification succeeded not because one man was smarter than Chrysler's engineers, but because the system allowed practical knowledge to challenge theoretical expertise, permitted bottom-up innovation to supplement top-down design. The Sherman would continue serving in armies worldwide for decades after World War II, fighting in Korea, Vietnam, and Middle Eastern conflicts through the 1970s. Its longevity testified to design philosophy that prioritized reliability and adaptability over technical sophistication. The stupid cooling fix that a factory worker proposed in 1942 remained in every Sherman produced, a permanent improvement embedded in machines that outlasted their designers' expectations and their opponents' supposed superiority. Walter Kowalski returned to automotive work after the war, spending another 2 decades on Detroit assembly lines before retiring in 1965. His contribution to Sherman tank reliability appeared in no history books, earned him no lasting recognition beyond the War Department commendation that hung framed in his living room. He attended veterans' reunions occasionally, meeting tank crews who had fought in Europe and the Pacific, men who didn't know that the factory worker who shook their hands had contributed to their survival through a modification they never saw. The broader lesson of Kowalski's cooling fix took decades to fully integrate into military procurement doctrine. The Pentagon, studying why American equipment reliably outperformed technically superior Soviet systems during the Cold War, eventually codified principles that Kowalski had demonstrated intuitively, that practical feedback matters more than theoretical perfection, that reliability multiplies capability, that systems should be designed for sustainability under actual operating conditions rather than optimal performance in controlled testing. Modern military equipment acquisition incorporates rapid prototyping, user feedback, and continuous modification, processes that recognize the gap between engineering theory and combat reality. These practices trace lineage to lessons learned in World War II, when factory workers and frontline soldiers contributed innovations that transformed adequate equipment into reliable systems. The institutional memory is imperfect, the individuals are forgotten, but the principles persist. The Sherman tank itself survived in various forms until the 1970s, serving armies across 6 continents in conflicts that bore no resemblance to World War II. Its longevity testified to design philosophy that valued adaptability and reliability, that accepted incremental improvement over pursuit of technical perfection. The tanks that outlasted German Tigers and Panthers did so not through superior firepower or protection, but through the cumulative advantages of systems that worked consistently under sustained stress. Walter Kowalski died in 1987, 2 years after attending the 40th anniversary reunion of the 2nd Armored Division, where he met veterans who had driven Shermans across North Africa and into Germany. They thanked him for his work building tanks, never knowing that the cooling system that kept their engines running owed existence to his graph paper sketches and practical understanding of how air moved through hot metal spaces. The war taught many lessons. Among them, that genius emerges not just from universities and engineering bureaus, but from factory floors and frontline trenches, that the men who build and use equipment understand things that designers cannot calculate, and that sometimes the stupid fix, the one that ignores theory to solve practical problems, is the smartest solution of all.